In section 1.5, we're going to review inverse functions. The intuitive concept between a function and its inverse is that whatever one function does, the other function kind of reverses it and does the exact opposite. For instance, let's suppose we have two functions. Let's call them f and g in the beginning, and suppose that they satisfy the following functional relationships. If you do f composed with g of x, if that gives you x, and if you also do g composed with f of x, and that also gives you x, then we say that the functions f and g are inverses of each other. And whenever that is true, instead of typically calling it f and g, usually we'll give the notion, we'll call g f inverse. Okay, so this notation here, be very careful. This is read f inverse. It's the inverse function for f. It does not mean -1 power, which would be like a reciprocal, like a 1 over thing. This is strictly used to denote an inverse function. We can rewrite that composition, rewriting it using this new notation. We say that a function f and its inverse satisfy the following property. When you compose those two in any order, you always get kind of the original input back. Okay. As an example, just kind of a simple example to highlight this compositional relationship, let's take a look at these two functions. The function which is multiplying by 2, and I'll just call it g for the moment, the function that is dividing by 2. We know from basic arithmetic that multiplication by 2 and division by 2 are inverse operations. So for example, if I start with the number x equals to 5, if I take 5 and plug it into f, we would get the output of 2 times 5, which would give us 10. If I then take that output, which we're calling g of f of 5, and plugging it into g, then what we would get would be 10 divided by 2, which is 5. So our final output is equal to our initial input, and the reason for that is that these two functions, f and g, are inverses of each other. Whatever one function does to an input, the other one would do the exact opposite to its output, and it would return the original value unchanged. In example 1, we're asked to show or to verify that two functions are indeed inverses of each other. In order to do this, what we need to do is check the two compositions and show that the two compositions would both return x. So let's begin by doing f composed with g of x. This is going to be f of g is the cube root of x plus 1 divided by 2. So I'm going to just copy down the statement form for f. F as a function says to take my input, cube it, double it, and then subtract 1 from it. Well, specifically what I'm plugging in is the function g. So I'm substituting in the cube root of x plus 1 divided by 2. And then from here, we want to be really nice and careful with our algebra, just so we are able to highlight and truly understand how these two functions are, inversing each other. First of all, the cube root and the cube will cancel. That would give us twice, no root anymore, twice x plus 1 over 2 minus 1. Next, the multiplication by 2 and the division by 2 cancel. So we get x plus 1 minus 1. And then the positive 1 and the negative 1 cancel, and we do get x. So we checked, and f composed of g of x does equal to x. However, we also need to show that the composition in the other order also gives us x. Now we're going to look at g of f of x. This is g of f was 2x cubed minus 1. The inner function is the f, the outer function is g. Let me just copy down the statement form for g. G as a function says to take my input, whatever that input is, I add 1 to it, divide by 2, and then I'm going to go ahead and take its cube root. Well, what am I using as my input for g? I'm using f as its input, So I have 2x cubed minus 1 here. And now let's simplify. The negative 1 and the positive 1 cancel. So we get the cube root of 2x cubed over 2. The multiplication by 2 and the division by 2 cancel. So we get the cube root of x cubed. And then lastly, the cube root and the cube cancel, because those are inverse operations. And then once again, we do get x. By showing that both of these compositions produce x, we have verified that G is indeed the inverse of F. So verifying two inverses isn't bad, it's just a matter of checking the two compositions. Let's suppose that we start with a function and we're asked to find its inverse when it has one. The steps in order to do this are as follows. We want to first of all begin by kind of reverting back to the old school notation. Instead of calling it f of x, let's replace that with y. From there, we are going to interchange and flip-flop the x and y variables. We're going to go through our equation, and everywhere you see an x, replace it with y, and everywhere you see a y, replace it with x. From there, we're going to solve this new rewritten equation for the variable y. This y, once it's solved by itself, it's not the same as the original function's y, which was f of x. This will now actually represent the inverse function, and it will be f inverse of x. Let's take a look at example 5. We're asked to find the inverse of f of x equals the square root of 7x minus 5. So let's go through this one. First thing we do is let's revert to the y notation. We'll call it y equals 7x minus 5. The next thing we're going to do is do this interchange. Every y becomes an x. Every x becomes a y. And now the third step is we now want to take this equation and we want to solve to get the y by itself. First thing we're going to do is square both sides. We get x squared equals 7y minus 5. A little bit of baby algebra here. Add 5 to both sides. We would get 7y equals x squared plus 5. And then the last step would be to divide by 7. So we get y equals x squared plus 5 divided by 7. And that's it. So this expression now, this y equals, that is our inverse function. F inverse of x is equal to x squared plus 5 divided by 7. If we're unsure of our answer, and this is not a bad thing to do, we can always go ahead and check this by forming the two compositions and showing that they both give us x. Let's actually go ahead and do that. So we said that f of x was the square root of 7x minus 5. F inverse of x we're claiming is x squared plus 5 over 7. Let's look at this composition first. We'll do f of f inverse of x. My inner function is f inverse, and I'm plugging that into f. So I'm just going to write out the statement form for f. F looks like this. It's 7 times input minus 5, and then take the square root. Well, what I'm plugging in is going to be x squared plus 5 over 7. First thing, the 7's cancel, multiplication, division. We have x squared plus 5 minus 5. The plus and minus 5 cancel. And then we have the square root of x squared, which will cancel and give us x. So that's good, that checks out. Let's now do the other composition, f inverse composed with f of x. Here the inner function is f, the outer function is f inverse. So I'm going to begin by copying down the statement form for f inverse. It's input squared plus 5 divided by 7. And what I'm substituting in here is f of x, which is the square root of 7x minus 5. The square root and the square cancel. So I get 7x minus 5 plus 5 divided by 7. The minus 5 and the plus 5 cancel. So we get 7x over 7. And then the multiplication and division by 7 cancel. And again, we do get x. So we have verified and proved that we did find the correct inverse. One of the things that's important to understand is that not all functions have inverses. Okay? The only functions that have inverses are those that are what we call one-to-one. If a function is one-to-one, then it has an inverse. Okay? And a graphical way to kind of determine whether this is the case is what's called the horizontal line test. What the horizontal line test says is the following. A function f has an inverse, f inverse, if there is no horizontal line that intersects the graph of the function of f at more than one point. For instance, if I look at this first graph, this graph would pass the horizontal line test. No matter what horizontal line you try to draw, it will always intersect the graph in at most one point. The implication of that is that this function is one-to-one, and therefore it has an inverse. On the other hand, if we look at a nice graph, just our basic x squared graph or something similar, this graph would fail the horizontal line test because there exists horizontal lines, or at least one horizontal line, that intersects the graph in more than one point. The implication there is that this graph is not one-to-one, and therefore it does not have an inverse. So the big takeaway for us is that a function has an inverse if and only if it is a one-to-one function. And the easiest way oftentimes to determine whether or not a function is one-to-one is to graph it, visually look at the graph, and then apply the horizontal line test. In example 2, we're asked this very question, which function has an inverse? The first one is f of x equals x cubed minus 1. This is one that hopefully from things we've looked at already we can do in our head. We should all know the parent graph of x cubed, and this is simply a transformation, it's a shift down one. So without technology, you should be able to graph this. X cubed looks like this, and this is a graph that would pass the horizontal line test. So we could say that it is one-to-one, and therefore f of x does have an inverse. And if you're trying to explain your reasoning, we would be quoting by, I'll abbreviate it, the HLT, horizontal line test. Let's take a look at another one. So this one here is yet another third degree polynomial. It's x cubed minus x plus 1. The thing you would want to do would be to graph this. Because of the presence of the x variable here, this added x, it's not simply going to be a transformation. So you might want to use some technology to do this. We'll actually learn how to graph these things by hand later on in the class. But for right now, just plug it into your calculator. And what you would see is it's going to look something like this. Okay. So it has the overall shape of x cubed, but with a little extra squiggle. And as a result of it, this graph is going to fail the horizontal line test. There exists at least one horizontal line that crosses the graph in more than one spot, and so this graph is not one-to-one, and therefore it does not have an inverse. So it does not have an inverse. And again, our logic is by the horizontal line test.